Okay, so all the exams should be graded up on Canvas, and then I built in so that it's reflected in the grade. So everybody's exam is kind of weighted by 30% right now, kind of treating it as though it's your best exam. Obviously, it may not be. We still have 2 left. But for the sake of how I have to kind of display it on Canvas, that's how I'm going to treat everyone's for right now, since we only have the first exam score in. If you have any questions over kind of the grading or anything like that, please reach out in like the near future. Like, don't wait for 3 weeks and then come to me with a question about it. So that Learn Smart I got posted up there on Monday as well. That's not due until we start class next Monday, so you've got some time to get on, kind of get that done. Other than that, any questions for me before we kind of get started on the new material today? All right. So we left off kind of talking about the uniform distribution and then just thinking about continuous random variables in general. So today, I'm going to start out talking about Carl Gauss. Basically, really smart guy, did a bunch of stuff, right? He was involved in a lot of stuff, just kind of like people of that time. You know, he had his hand in just about everything. But along with another, I guess, mathematician, he came up with or discovered kind of this normal distribution. All right, so we'll be using this a lot for pretty much the remainder of the semester. And this normal distribution is sometimes referred to as the Gaussian distribution because he was kind of one of the primary individuals that helped kind of discover. So I think who knows if this is actually a true story, but the story about Gauss is that, when he was a kid, he's misbehaving, real young kid. Teacher told him to go in the corner, add up the numbers from 1 to 100. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus all the way up to 100, right? He comes back in a matter of seconds, right? The teacher thinks it's going to take him forever, kind of get him to calm down, and he has the answer. So how did he come up with this so quickly? And this kind of highlights maybe, I don't know, how these mathematicians, even when I hear this, like my brain just doesn't work this way. But basically, if you think about, you have all these numbers and you're trying to add them up, what would 1 plus 100 be? 101. 2 plus 99, 101. 3 plus 98, 101. Basically, you can do that all the way down till you get to 50 and 51, which add up to 101. And you'd have 50 pairs of 101, so 50 times 101 is just 5,050. So what he was actually thinking, there's an actual formula for this you can use if you want to add up 1 to whatever number n, and then you would just be plugging n in here. But this kind of thought process is kind of how his brain worked. So really, really smart guy. And this normal distribution ends up being important for us when we're doing a lot of different things like hypothesis testing once we get to linear regression. So this is really going to be kind of the fundamental distribution that we'll be using. Right? So we see it pop up in nature a lot. So just a couple of the variables. I have human height, rainfall here. If we look at weight, if we look at temperatures in the same area, we see that they typically follow kind of this normal distribution. A lot of things in nature do. If we look at biological markers, like every species, their size kind of follows a normal distribution. If we look at human performance, which I don't know if we'll have time at the end, I might show you some that are kind of interesting to see where the normal distribution pops up. But we see it occur in biology and kind of in nature a lot. Right? So this is kind of the book they published, which was recording all these things like rainfall and human height and kind of realizing they all had the same shape distribution, right? The shape of this distribution could be explained by a probability density function. So I already mentioned this kind of applies to regression. So this probability density function looks real nasty, right? We're not going to have to do anything with this, but I want to point some things out kind of moving forward to think about the normal distribution, which is that really if this probability density function is supposed to be that if I'm plugging in different values of x, I can get what the probabilities are of those values, right? Or I can use this to determine the probability over certain intervals. We talked about last class. Technically, the probability of any one value should just be 0, but we can find the probability over certain intervals. Right? What's the probability I see x be between 2 and 3.5? Now notice it's got the things that kind of define this normal distribution are the mean and the variance, right? Sigma squared and mu here. We'll talk about how changes in the mean and the variance would change our normal distribution in just a second. But it also, so it's not only kind of defined by the mean and the variance, but also notice we have those two natural numbers, pi and then an e, kind of pop up here. So two of these numbers that, have been kind of have a reputation for being really unique, right? Or properties that we're not sure, the decimals of pi kind of continue off of infinity. They end up showing up in this equation that we see pop up in nature a lot. Right? So kind of interesting there. So if we think about the characteristics that this normal distribution is going to have, or this probability density function will have, right? It's going to be symmetric such that if we look at the mean, that's going to be the same as the median, which means that mean exactly splits kind of this distribution in half. So there's 50% of the observations to the right of the mean, 50% to the left, right? Because the mean ends up being exactly equal to the median for this normal symmetric distribution. So it's defined by the mean, it's defined by the variance, right? So we can think about some examples of this. So let's say I had, maybe I'm thinking about human height, right? And I know that it varies across the world. So maybe I go to different countries, and I don't know, maybe I go to the US first. I determine kind of what the distribution of height looks like, and I find that it has this mean mu2. Right? And then I go, I don't know, to some other, let's say, I don't know, Canada or something. I get their height, right? I find that they have a slightly lower mean or a slightly lower average height than the US. So the distribution, if it had the same variance, would look the exact same. It's just the difference in mean will shift that distribution, right? If they have a lower average, it just shifts that entire distribution. And then, I don't know, maybe I go to Mexico and they kind of have a higher kind of average height, that would shift the distribution to the right. So the mean is just going to shift my distribution along that x-axis, while as the variance is a little bit different. So for the variance, try to give you an idea visually here what's going on with that. Maybe. There we go. So let's say I'm looking at this variable x. And I don't know, this could be, you could think about rainfall, and maybe we're looking at rainfall in different months. So maybe the first month we look at, we plot the distribution. It's this nice normal distribution, and it has a variance of, I don't know, 5 inches of rainfall, right? It's got some mean. We'll call this group 1 or distribution 1, month 1, whatever month we're looking at. If we then look at a different month's rainfall, and here I wrote this as the standard deviation. It doesn't matter if we're thinking about variance or standard deviation, right? The one is just the other scaled. So if it has a higher variance or a higher standard deviation, that month's distribution of rainfall, what that higher variance is telling us is that the data is more dispersed, right? That it's less likely for us to see something near the mean and more likely for us to see something further from the mean. So if we think about this the y-axis, kind of representing the probability of x here, a higher variance or a higher standard deviation means the values that are further from the mean, right, are more likely. So the values further from the mean are more likely, and that the values near the mean, right, are less likely. So our normal distribution would look like a flatter curve, right? I didn't draw this real great, but I'm going to try to get it to be a little bit smoother here. Right? So it's still symmetric, right? It's just flattened out, right? So the higher the variance or the higher the standard deviation, the flatter our curve is going to be. If the variance gets lower, that means it's more likely we see values near the mean, and so we get this more peaked distribution, right? Showing us that, you can imagine like a really extreme one. Maybe it's something like that, right? Where the probability of seeing these values near the mean is really, 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 really high up here, okay? Any questions on that? So we've got the mean that shifts this distribution to the left or the right, and then kind of the variance will tell us if it's flatter or kind of more peaked. Right? So that's what this is kind of showing, right? If we had multiple distributions here, a little bit cleaner of a drawing, but as the variance gets higher, we get a flatter distribution because it means that when the variance is high, the probability of seeing values near the mean is a lot lower, right? A lot lower than when the variance was low. Okay. Any questions on that before we keep moving? Okay with that? So, if I looked at something like this, and this is somewhat, was taken from a smaller data set, but it's still kind of reflective of what we see when we look at larger data sets that get closer to the population. But if I'm looking at this, we'll look at it here in class in 1 second. So if I'm looking at this distribution of male and female height, which one of these has a higher mean? Well, if I try to look at where's the symmetric point, where would exactly split this distribution in half? So somewhere down here around 65. And the male distribution, it's going to be somewhere around 71. Right? So if I look at that, I can kind of compare where's that point where that distribution would fold on top of itself, right? Where is it symmetric? Well, that's the mean and the median. And I can see that's a little bit higher for men than women here. If I look at these two distributions, which height has more variation in it, male or female height? So which of these is flatter, right? That's kind of the male distribution, right? It's shorter, it's flattened. So if it's more flat, right, if it's going to push towards the x-axis there, we know that we have if it's flatter, that means that it's more dispersed, so it has a higher variance, which means that it's less likely we see values that are around the mean, which would mean that the probabilities would be lower or kind of squish that distribution down. So this would kind of, just looking at these two distributions, we can say that male height has a little bit more variation to it than female height. Okay? Any questions on that? Another thing to point out here when we start looking at distributions of these different variables, once we have the entire distribution, it's, we're going to make statements a lot of times like, there's a difference in the means here. So males are on average taller than women. But when you draw the distributions, this also tells you that, look, all these, right, these represent, here I've got frequencies, right? This was coming from a data set, but we can easily turn frequencies into probabilities by dividing by the total number of observations. And what this is really saying is there's people, right? There's males who are kind of at these height levels, which would be then shorter than any female that's kind of over here at these height levels in the female distribution. So if we have overlap in the distributions, yeah, on average, males would be kind of taller than females, but for any two individuals we compare, all bets are off, right? So it's kind of the things we'll start thinking about when we have these distributions is that we make statements in generalities, but right, we can think about, well, for any two individuals, right, there could be a completely different relationship. And we even get to a point where maybe we say, okay, what's the probability that if I choose two people at random, even though these means are different, what's the probability that we might see them kind of have the female have a higher height than the male or things like that. Right? So that's kind of where we're going. But we need to understand a little bit more about the normal distribution and a little bit more about one specific type of normal distribution. So just like for uniform distribution examples, and really the way I set up any continuous random variable, the area under this curve is 1. Oops, sorry. So if we looked at kind of integrated this function from the very lowest to the very highest x value, the area under that curve would be 1. Right? Now that would not be fun to have to start, where is it at? Integrating this function, all right? So, oops, keep going here, there we go. We're gonna start to wanna think about how can I turn this, how can I make this normal distribution easier to work with so I don't have to do all this integration? Well, one thing that ends up being true, and by the end of today's class, hopefully we'll have kind of worked through and I can kind of prove this to you, if not for sure on Friday, is that if I go one standard deviation below and above the mean, right? So I just go one standard deviation above and below, the probability I see the variable x take on a value in between that range is always going to be 68%. If I go, so the probability I see something in between one standard deviation above and one standard deviation below is 68%. The probability if I go two standard deviations above and below the mean, the probability I see a value, this random variable x take on a value in that range is almost just above 95%. We go to 3, it's up to almost, it's above 99, almost 99.9% there. So we can start to think about, where are these values coming from, right? I have that probability density function. I could plug these values in as my minimum max, integrate the function over that range, and it should return to me this value. But I don't want to do that every single time, right? That's kind of a pain to integrate that function. So what do we want to do? Well, we know that normal distributions, like two variables can be normally distributed, but have very different means and variances, right? Human height is going to have a very different mean and variance than rainfall, right? First of all, they're even in different units, right? So how can I convert a normal distribution into something that's a little more easy to work with, which would be this standard normal distribution. So the way that we typically write these random variables is, here's this random variable x, it's distributed normally, so n here's normally. Last class we had a u here, that was uniformly. So now this is normally, here's its mean, here's its variance. So the standard normal distribution, it's the same thing, but it has a mean of 0 and a variance of 1. Okay? So mean 0, variance of 1 will be that standard normal distribution. Okay? So why is this helpful? Well, if we think about it, right, if I'm looking at this variable with a mean of 0 and a variance of 1, if it has a variance of 1, what's its standard deviation? Yeah, square root of 1 is still 1. So this is a really unique distribution in that the variance and the standard deviation end up being the exact same value, right? Because it's always going to be 1 if it's standard normally distributed. So I can start to interpret kind of any value I see for x. Let's say, before I get here, let's say I see that this standard normally distributed variable, I look at x, and x is 3, exactly 3. Well, what that would represent to me is 3 would be how many standard deviations away from the mean? Well, the mean is 0. Standard deviation is 1, so the value of 3 is 3 standard deviations away from the mean. What if it's 1.5? Well, the mean is 0, so seeing an x value of 1.5 means I'm 1.5 standard deviations away from the mean, because that standard deviation is just 1. So a standard normal distribution, the values will have this really nice interpretation, which is whatever the value of x is, that's just the number of standard deviations away that value is from the mean. So if I can convert any normal distribution into a standard normal distribution, the value I convert it into should just reflect to me how many standard deviations away from the mean whatever value I was looking at is. So how can I get this? So, we think about these different values, we'll start calling them z values if it's coming from a standard normal distribution. Instead of thinking about it as x, we'll start kind of thinking about it as z, right? And we'll start calling these z-scores, right? So a z-score of -2 means I'm 2 standard deviations below the mean. Okay? I'll hold off on 1 second. So let's say, how do I make this conversion of the original x variable into a z-score? Right? So the process by which we'll do that is we'll look at whatever the x value is. So maybe we're looking at, human height, and I see someone is, 63 inches tall. How many standard deviations away from the mean is that? Well, if I take that 63 inches, I subtract the mean height and divide by the standard deviation height, I will have then converted that into a z-score, which will tell me how many standard deviations away from the mean was that value of 63 inches, right? Or if I have someone who's, or the value of 70 inches tall, I would take that 70 inches, subtract the mean height, divide by the standard deviation of height, and that would convert it into a z-score, which would tell me how many standard deviations away from the mean is that value of 70. So this is kind of the interpretation and the usefulness of z-scores. They get a lot more useful, we'll see, but for now, that's what we're thinking about. They we're converting our original x variable so that it has the translation of how many standard deviations away from the mean it is. Right? So, you think about for the mean, how many standard deviations away from the mean will the mean be? It's exactly the mean. It's 0 standard deviations away from the mean, right? So that z-score for the mean will always be 0. Think about it. If I plug the mean in here, the mean minus the mean is 0, I'll always get a z-score of 0. Right? So anytime I'm looking at the mean of this normal distribution, when I'm converting it into a z-score, that mean should always have a z-score of 0. And then if I have, something that's positive, that's telling me it's a certain number of standard deviations above the mean. Oops, if I have an x value that's negative, that would mean that I'm a certain number of standard deviations below the mean. Okay? All right, so we've got this standard normal distribution, right? And it's going to have these this nice interpretation for us. Right? I'm going to go here and actually, I think what I want to do first, I'll actually just use Excel to show this to you because it's a little bit quicker and I think it really kind of hammers home the point, right? So let's say I have this variable x, right? I've got all this data. Now, I'm not going to make it a very big data set and it's going to be real easy, but let's just say it was 5 data points. And I go over here and I want to calculate the mean, and the standard deviation of x. Well, we know in Excel, hopefully at this point, we can use that average function to find the mean. And we'll treat this as population data just for the sake of making this a little bit easier to think about, but it doesn't matter if we do this the other way. So let's say we take the standard deviation, right? And I get my mean and my standard deviation of this data set. So if I turn this into z-scores, we said the equation for that is going to be, I'll take the x value, I'll subtract the mean, and then I'll divide by the standard deviation of my variable. So this is just simply converting that value of x, that value of 10, into a z-score. How many standard deviations away from the mean is that value of 10? So we get a z-score of 1.4, which means 10 is 1.4 standard deviations away from the mean. The mean of 6. It's 1.4 standard deviations away. Now, I could do this for my entire data set. Notice, I'll always want to subtract the mean, so I'm going to put $signs around that. Remember the shortcut for that, Command-T on a Mac or F4 on a regular kind of non-Mac. I then highlight my standard deviation. I always want to divide by that, so I'm going to freeze that cell reference. Now, when I copy this down, it'll convert all of my x values into these z-scores. Notice 10 was 4 above the mean, right? Which translated to 1.4 standard deviations. 2 is 4 below the mean, so that should be the same number of standard deviations, but negative, right? Because it's below the mean. So I've got my z-scores. What should be true, unless I was lying to you, is that the mean of our z-scores and the standard deviation of those z-scores should be 0 and 1, right? So if I try to find the mean here, I just take the average, using the average function in Excel, highlight my z-scores. I'm finding the mean of my z-scores. Sure enough, it ends up being 0. What about the standard deviation? This should be 1, so I highlight my z-scores. Sure enough, once I hit enter here, I get a standard deviation of 1. So you can walk through the mathematical proof if you want to. For me, seeing it play out in data is always like a lot more confirming to me, or reaffirming when I see that this actually works out. So creating these z-scores ensures that I'll have this standard normally distributed variable. Okay? Now, one thing that's I just want to point out here, and this is a little bit of foreshadowing, but when we think about when I started out here with, I tried to have something that would kind of resemble a normal distribution in the sense that it's symmetric, right? So if I start out with this symmetric normally distributed variable x, my z-scores, notice, are also symmetrically and kind of normally distributed there. Now, what happens if the original variable isn't symmetric, right? Well, that's okay, right? Creating these z-scores will still give me a mean and a standard deviation of 0 and 1. It's just going to make the distribution of my z-scores not symmetric, not quite normally distributed. But they would still have a mean of 0 and a standard deviation of 1. So this process of subtracting the mean and dividing by the standard deviation, we call that kind of standardizing the data, or kind of shifting the mean back to 0, and then kind of molding that distribution or altering that variance so that it is no longer 18 here, but kind of, what word am I looking for? Why am I blanking? Not converting it to 1, scaling it so that it's 1. Okay. Sorry, I don't know. I just said my brain was not working there. So, but with the original, we can see if it starts out symmetric, then the z-scores will also be symmetric, right? But they'll always have a mean 0 and a standard deviation of 1. We're looking at the z-scores. Okay. What we also can do is start to think about. I stole this from a book, but this is a really good overlay. If we go a certain number of standard deviations away from the mean, right? Why do those end up being, why is -3? Why does that z-score tell me that I'm 3 standard deviations below the mean? So if you think about what we're doing with this z-score, we've got the x value, we subtract the mean and divide by the standard deviation. Right? So let's say our x value we're looking at is 2 standard deviations below the mean, right? So it's 2 standard deviations below the mean. Well, once we plug that in, right, we've got what? The mean minus the mean, that cancels. My standard deviation will cancel, and I'll be left with that -2. So kind of plugging in certain numbers of standard deviations away from the mean, we can see that that's why our z-score can be interpreted that way. Because of the way that things will cancel, however many standard deviations above or below the mean we are, that's what the z-score is going to tell us. Right? So subtracting out that mean, dividing by the standard deviation. Okay. Any questions on this before we keep moving here? Shouldn't be too bad yet. Okay, so where are we at in time? All right, so why make this conversion? Yeah, the interpretation is nice, but how can we use these z-scores to make other things easier? Well, we talked last class about I can use this cumulative density function to find the probability that x is between a and b. Right? This was the idea that if I use that cumulative density function to find the probability that I'm less than b, and then subtract it out, the cumulative density function where I'm less than a, what I'm going to be left with is what's in between a and b. Okay? So, that normal distribution, if I have the density function, I can come up with the cumulative density function, but it's a mess. I don't want to have to integrate. I don't want to have to kind of deal with any of the mathematics or, the real kind of tedious mathematics. But we have a table where someone's already done all of this work because it'll always be the same. Once I get a standard normal distribution, the probability that I'm a certain number of standard deviations above or below the mean, that z-score, it'll always have kind of the same area under the curve up to that z-score, right? Because it's a standard normal distribution. It's always mean 0, variance of 1. So these tables will help us find things like, well, what's the probability that I see x be between a and b? We'll convert a and b into z-scores, and then we can use that table. So I'll show you the table. Well, I think I have it in a slide, so I'll hold off, and then I'll show you the one that I'll upload to Canvas. But let's say, I have some value. Let's say, I'm thinking about human height, and I look at the value of being 70 inches tall, and not said that would make sense in this context. 50 inches tall, right? And so, we'll do 60 because that makes a little more sense. So we'll do 60 inches tall. I convert that into a z-score, and I get -1.29. It's 1.29 standard deviations below the mean. Well, that standard normal table, I can look up that value of -1.29, right, if I plot that point, and it'd just be the area under the standard normally distributed curve from -infinity up to that -1.29. Right? Because theoretically, that can be however many number of standard deviations below it. So that's the area I want to find. How can I use that table to find that? Well, once I have my z-score, right, what's the probability that I see someone who's 60 inches or at least 60 inches or shorter than that, right? Or anyone 1.29 standard deviations below the mean or even further from the mean. Well, if I go to this table, I know this is a little bit small. I'll grab the file and kind of zoom in on things here. I've got these kind of column headings, and I've got these row headings. Okay? So I've got some of the steps for walking through it, kind of with some outlays here. but I'm just going to walk through the other one. I'm going to increase the size so it makes it a little bit easier to follow along with what I'm doing. And actually, I don't think I've dragged the file yet, so I'm going to go back here. So this is the file that'll be up on Canvas after today's class. We'll be using this a lot, so it might be helpful to kind of have it printed out with you to follow along, because in class or even via Zoom, like I can only make it so big sometimes and kind of show it as well as what we're doing, but it might make it easier to be able to have it right in front of you, or have the file so that you can kind of open it up if you're going to have a computer or something in front of you. So the way that we'll read this is, if I want to look up that z-score of negative 1.29, I'll go down here on the left-hand side, negative 1.2. So that's the kind of first decimal point of the z-value I'm looking up. I then go over to the column that has the second decimal point. So I'm going to be on negative 1.2, and then I go all the way over to where that second decimal is 9, right? Negative 1.29. So negative 1.29. Move this thing out of the way here, right? Once I kind of find find the number I'm looking for, that negative 1.29, this value is the probability that I see that z-score or anything below it. Or essentially, this is a cumulative density function table, right? Whatever z-value I look up, it's always going to give me the probability I see that z-value or anything to the left of it, right? Or exactly what I wanted here, right? The probability I see that z-score or anything below it, okay? Now, what should be true if anytime I look up a negative z-score, what should the probability always be less than? If I'm thinking about the area to the left of it, I know that for a negative z-score, that area always has to be less than what? So let's think about this standard normal distribution. So I've got my z-scores, right? I know it's a normal distribution, and because it's a standard normal distribution, I know the mean will be 0. What's the probability I see something to the right and the left of that mean? It'll always be 0.5, right? Because it's a symmetric distribution. So the mean is exactly equal to the median, and it splits this in half. So anytime I see a negative z-score, right, even if it's like negative 0.4, negative 1.29, the area to the left of it, of those negative z-scores, has to be less than that area of 0.5. Okay? Similarly, if I look at any positive z-score, what does that area have to be larger than if I'm looking up the cumulative density, right, or the area to the left of it? Well, it's going to include the area of 0.5 plus something else, so it's going to be greater than 0.5. So anytime I look at this z-score, if it's negative, the area to the left of it should be something less than 0.5, and if it's a positive z-score, the area to the left of it should be greater than 0.5. Sure enough, if I look at this table, when I look at all these negative z-score values, notice the area to the left of them are all less than 0.5. When I get to exactly 0, so 0.00, right, that's that column, the area to the left of 0.00 is 0.5, right? That's the mean. And then as I get values, z-values that are positive, notice all the probabilities or the area to the left of those z-scores are now all above 0.5, right? Because it's a cumulative density function. As I get to higher and higher values, that cumulative density should approach 1, right? Eventually, if I get high enough, it rounds to 1 to the 4th decimal point. Okay? So that's how we can start to think about this table. If I wanted to look up that z-value of not negative 1.29, so let's say now someone is 70 inches tall, and that is 1.29 standard deviations above the mean. Right? So what's the probability I see somebody at least 1.29 standard deviations, sorry. What's the probability I see someone 1.29 standard deviations above the mean height or anything below that, right? Anything to the left. So I go 1.2. Let's see if I can get this all in the same. Yeah, there we go. 1.2, Then I go over to the second decimal, which is 9, so negative 1.29. And the probability that I see something to the left of positive 1.29 is 0.9015. Okay, so just to kind of give you an idea here, I'll switch back and forth here in a second just to show you where I'm getting these numbers. So let's say I've got these z values. The first z-score we looked up was negative 1.29. And if we go back and look at what the table told us, I believe it's 0.0, what did I just say on that one? 0.9015, so 0.0985, I think is what it was. Let's double check. Negative 1.29, so yeah, 0.0985. So this was 0.0985. And then if I think about the area to the left of positive 1.29, kind of this total area was 0.9015. Okay. So notice, what do those values add up to? Actually add up to 1. So why did that work out to be that way? Well, if this is a symmetric distribution and I were to fold this right around that mean of 0, the area to the right of positive 1.29 should be the same as the area to the left of negative 1.29. So this area should just be 0.0985. Once again, if I've got the area to the right of 1.29, what does the area to the left have to be? Well, the area under the curve is 1, so it would just be 1 minus that 0.0985. Or when I looked it up in the table, it gave me that value of 0.9015. So just kind of trying to piece some of these things together where because it's a symmetric distribution, sometimes it makes life a little bit easier for me to think about these same z-score values, but one's positive, one's negative. Any questions on any of that before we keep moving? We're okay with that? All right, so that's our table. We kind of walked through it here, how to find different values. This is just kind of a visual that I just kind of had on the dot cam. It's not a whole lot different. We've kind of already talked about this. Now, if I start to think about some z-scores that are going to pop up a lot, so these are going to be kind of the z-scores we see a lot, and that's because they translate into some kind of nice benchmark values. If I go 1.29 standard deviations above the mean, the area to the left, or the probability I see that z-score or anything less, is about 0.9, right? About 90%. 95, 97.5, 99, 99.5. Right, so these are just going to be some benchmark values we see pop up a lot. I already kind of discussed this, right? If I can find the area to the left of 1.29, if I wanted the probability that it's greater than 1.29, well, the table always gives me this cumulative probability, or the area to the left, right? The probability of seeing that z value or anything below it. So to determine what that is in that tail, I'd have to take that area to the left and subtract it from 1, which gives me that 0.0985. So I kind of already walked through this as well, but this slide is kind of a reminder of that. Okay. I already mentioned this as well. A lot of the times we can make sense, or we can like bound where the answer should be by remembering that this is a symmetric distribution, 50% or the area of 0.5 to the left of the mean, and an area of 0.5 to the right of the mean. So these are all things I've already kind of pointed out here. So you can kind of see if I try to put this in the slide, this is just really, really small value, or this ends up being not small value. This is just a really, really small picture, and it's hard to grab the values from it. So having your own kind of version printed out, or at least have the PDF on your computer or something that you can pull up will kind of help you follow along a lot more in class when we're dealing with this. Okay? So if I had maybe a normal distribution example, maybe this would be on a question like on the online quiz today. What if I wanted the probability that z is greater than or equal to negative 2.53? Well, first of all, let's just draw out what this would look like. So a lot of times drawing things out is going to help you eliminate some answers really quickly, and at least just get an idea about the ballpark for where that probability should be. So I had these z values. If I wanted the probability that I see negative 2.53 or greater, what do I know that probability has to be greater than? I'm looking at z-scores. What's the mean of that distribution? Standard normal distribution, so the mean is, 0. What's the area to the right of the mean? It's always 0.5. Right? So I know the probability I see the z-score of negative 2.53 or greater has to be greater than that 0.5, right? It includes that area plus some more. So just drawing it out right away, we can kind of figure out that what? B doesn't make any sense. C definitely doesn't make sense, right? It's not even, we're looking for a probability between 0 and 1. Now, we're probably not real familiar yet with these z values, but remember, I was saying once we get to 3 standard deviations away from the mean, or a z-score of -3, 99% of the data is in between 3 standard deviations above and below. So, seeing something that's even further than 3, just very, very unlikely. Well, 2.5 standard deviations away is pretty far, right? Now, like I said, we're probably not like used to knowing that that's very far. As we work through more examples, we'll be able to start to think that, okay, that probability is probably closer to 1 than it is going to be to 0.5, right? The z-score, such that the area to the right of it would be 0.5057, would have to be, well, look, the area to the right of 0 is 0.5, so the z-score we would need to be just over an area of 0.5 to the right of it would be something like, negative 0.1 or something really close to 0, right? So if I'm guessing, right, by the time I get out to negative 2.53, that probability is probably going to be pretty close to 1. Okay? But how can I actually find that? So we'll go to my table. We've got negative 2.5. Let me scroll up. Maybe we can get everything. Here we go. Negative 2.5. 3 was that second decimal, so negative 2.53. 0.0057. Right? Okay, so that's my answer. Well, no, right? Because 0.0057 is the area to the left of that z-score. I wanted the area to the right, so what do I need to do? Well, the area under the curve is 1. So if I want the area to the right of that, it's just 1 minus. Okay? So what, 0.9943 or something really close to 1. Okay? Any questions on that? Let me see if this helps. I feel like this looks a little bit blurry, but I don't know where the remote to it is. All right, so what if I wanted the probability that it's less than? Well, we basically found this in the process, right? If we wanted the probability that it's less than negative 2.53, that was simply looking up negative 2.53, and the table gives me that area to the left is 0.0057. So I kind of guessed wrong this week. I'll have to kind of repost these slides and add a bunch more, more material. Or we might be doing a little bit of stuff in Excel, but I think before we get that, there's some more that I want to kind of discuss. So Friday we'll have some more normal distribution stuff. But one thing that I did have these at the end because I think it's relatively interesting. So I had this data set that had like a survey of like 12,000 different individuals, and it had their recorded height. So I pulled out, I forget if this was, well, we can probably figure out 70 inches. So I'm guessing this is the male height that I pulled out, right? Because if we include both of them, we talked about, I'd probably end up with like this bimodal distribution. So you can kind of see, it's not perfect, but if I try to draw a line through this, it's really, really looks like a pretty symmetric distribution and pretty close to a normal distribution. So here we kind of see it playing out in human height. This is one I thought was really interesting. I don't know why I was following this. Well, I do know why, but anyways, I have this, I was following this thing on Instagram, and it was affiliated with CrossFit, and so they had like some of the results from their CrossFit open workouts or whatever they are, and so they just kind of showed it, and I don't remember what they were geeking out about, but when I saw it, like I was geeking out about how like the female performance in whatever this event was, I mean, this is almost a perfect normal distribution. I mean, I couldn't draw it probably closer, right? So that's why I was saying a lot of times in these biological things or like these human performance measures, we start to see a lot of normal distributions pop up as well. Maybe the males here, there wasn't quite as perfect, but it's still pretty close, right? So I thought that was kind of interesting that we see it pop up in this random, like, I don't know, working out thing. And then I had some powerlifting data where you can kind of look at, these are a little bit skewed, but even here we have human performance that's really close to a normal distribution. We think about how much weight kind of the female and the males were deadlifting. We get this really nice kind of normal distribution. I also thought it was kind of interesting. So you look here, like where would the mean be? So the mean's like 300 kilograms and about 600. So the male looks like there's a much higher mean. So, if you took this data and we're like, oh, men are way stronger than women, you're like, well, here's the data that backs it up. Well, what's interesting is if you think about how much weight someone's lifting depends on how much weight they weigh, right? And I started looking at the data set. There's a lot more 300 plus pound men than there were 300 plus pound women in the data set. So like, this isn't really apples to apples. So there's this thing called the Wilks, which essentially takes the weight lifted and divides it by kind of your body weight. So it gives you more of like a per pound strength measure. And if we look here, once again, pretty nice. I mean, the male distribution here is like a perfect normal, maybe a little bit of skew here on the female one, but really close to normal distributions. But notice if I try to look for the mean now, it's around, 300, 350, maybe high 300s. And then over here for the men, it's in the high 300s, right? So you actually get that kind of per pound. There's not a lot of difference in strength between kind of males and females by using that Wilks measure where you divide by the weight. So I think it's kind of interesting just in the general discussion of statistics, right? If you don't have the right statistic or you don't think about, what's another factor that might be influencing the kind of female weight lifted and not the male, well, it's that this group is just heavier on average. Once you account for that, you get that there's kind of strength measures are pretty similar between the two genders, which I think is kind of interesting. Okay. All right. Well, that kind of does it for me today. We'll continue with the standard normal distribution. I'll get that table posted up on Canvas. We'll just go through more examples. We're going to start getting used to using that table. And then I don't know if we'll do it Friday, but for sure on Monday, then we'll kind of transition to how do we do some of this in Excel. Right. Once we get a good idea about how we're working through some of these problems by hand, we'll then kind of move to see how we do it in Excel. Okay. All right. Well, enjoy the beautiful weather, and I will see you guys on Friday.